Thank you for joining me, everyone, in my living room. My son Calvin is filming us today. So we're going to review a little bit of a few things I wanted to cover before we move on to the mean, which is where we left off with measures of central tendency. This was the distribution of ages of class members. And in class we created a frequency distribution, which you can see right here. We had one 18-year-old, four 19-year-olds, seven 20-year-olds, three 21-year-olds, one 22-year-old, two 23-year-olds, and one 29-year-old. What?
Scoot back a little bit. That way.
Why?
Okay, because you're in frame.
Oh, okay. Anyway, and we determined that the modal age, or the modal category of age, not category, the modal age is 20. This is an interval ratio level of variable, and in terms of level of measurement, what else did we determine? We determined the percent for each of the different ages, and again, we took raw data and we made it into a frequency distribution. I just want to show you a few examples of how you could graph this kind of data. Probably very familiar to all of you, but I just want to demonstrate what it would look like with this particular data. So there are a couple different graphs that you'll see most often, the first one being just a simple bar graph. So you would have, this is your y-axis, which is always your vertical axis. Calvin, can you make sure that the camera's picking up this? An x-axis. Are we good? Okay. And so this is always the axis that's going to tell you the number of people. So this is always going to be the number of cases, basically. And for a basic bar graph, you have your, and just as really important, usually bar graphs are used with nominal level variables where you have categories. But they can be used if you just have a few sort of age values that you want to do. So you could have 18, 19, 20, 21, 22, 23, 29. And so for 18, so we go from 0 down here, from 1 up to 7. So we have one person at 18, we have 4 people at 19, we have 7 people who are 20, and so on. Very straightforward. I don't need to fill out the rest of this. So this is a histogram. I'm sorry, that's a bar graph. A histogram, the only difference between a histogram and a bar graph is a histogram connects these together. So instead of having them as separate bars, you would have like this. Minute point, but you'll hear the two terms and you'll wonder what the difference is. It's simply squishing them together versus having separate bars. Both bar graphs, histograms, are used with nominal level variables, ordinal level variables. Typically when you have interval level variables, you're going to see more of a line graph because it represents, is an easier way to represent a. Okay, so we talked about bar graphs, histograms, which are good for nominal and ordinal level data. Technically, we have interval level data, and the best way to depict that in graph form is through using a line graph. So I've drawn this out. We still have the same y-axis going on where we have, this is a reflection of the number of cases that we have. And our x-axis represents the variable that we're interested in. In this case, it's the age. I've put tick marks for ages starting with 18, going straight all the way to ages, all the way up to 29. I left out everything under 18 because we don't have any cases there, and it's just easier to start there. So all I'm doing is putting a dot to indicate the number of people who are 18. the number of people who are 19, the number of people who are 20, the number of people who are 21, the number of people who are 22, 23. Now we don't have anybody who's 24, 25, 26, we said, so that's going to be 0, but then at 29 we have 1 person. And typically we would see a line connecting those dots to give us a sense of the flow of the data, the direction of the data. And this will make a lot more sense later as we talk about how distributions are shaped and what that shape tells us about the distribution. What we can see here is we have one sort of outlier case in our distribution, and most of the others kind of sit right around here. And this makes sense because we know that our mode is 20, which is sitting obviously right there. And our median was 20, I think, as well. So that also makes sense in terms of visualizing the graph. Okay, so we'll hold on that for a minute, but I just wanted you to see how you would graph a frequency distribution. I'm going to pull out the PowerPoints which you have at your disposal. So this is actually the PowerPoint from the 16th of January, which we didn't ever finish. So our third measure of central tendency is the mean. If you remember, we looked at the mode and the median, and we learned that certain of those are more appropriate for certain levels of measurement. The mean is only appropriate for interval level variables. It is not appropriate to be used for ordinal level variables. It is not appropriate to be used for nominal level variables. Some researchers do it anyway, but it's only, for our purposes, I want you to know it's only for interval level. So here's some key points about the mean. One important thing to know is that it uses every data point. It is the average, the mathematic average of all the data points. It's because it uses all of the data. It's the most popular and widely used measure. As we said, it requires interval ratio level variables. Down here I already said how all values are used in its calculation. It's unique in that there's only ever one. You only have one mean, unlike, say, with the mode, where you can have 2 modes. One distinction that we'll make here, starting here, and you'll see this again and again, is that we have a symbol for the mean, which is this X bar. And we can also sometimes see the symbol called mu, it's a Greek symbol, look like this in red. And the difference between the two is that you use the X bar when you're talking about the mean of a sample, and you use the mu if you're talking about the mean of a population. And if you remember, a sample is just a small group pulled randomly from a population. And so we'll be going back and forth between what it means to have a mean or any other kind of statistic, but in this case, a mean versus a from a sample versus the population. Another key point to remember is the term parameter versus statistic, and we did say that a statistic is a measure from a sample while a parameter is a measure from the population. So the mean is a measure of a central tendency, and when we use X bar, that's our statistic, and when we use that mu, that's our parameter. Okay, and don't let these formulas scare you, but they're very straightforward, and they basically show us that, and they're exactly the same. The only difference is this is the X bar, this is the mu symbol, but they're the same formula. Oh, and this is a big N and this is a little n. The big N means it's a population. The N is the sample size. That's what that is. The X is each value that you're talking about. So for every value, this is the summation sign. You're adding up every value in your distribution of your data, and you're dividing it by the number in your sample, or you're dividing it by the number in your population. So You've all calculated an average before. That's all that is. So let's look at that as an example. Here's back to our example of 14 different students who have spent varying amounts of money on books for a particular semester. And essentially, in order to calculate the mean, you're going to take every single one of these values and take the sum of all of them and divide by n, which is 14, because that's the number of students we have. And we get 335 as our answer. So you should be able to calculate that by hand. And we're going to do an example of that using a frequency distribution. This is just raw data. But it's the same idea with the frequency distribution, it's just that it's grouped and organized for you. So here's a frequency distribution to look at. This variable is number of siblings. That's the name of our variable. So the different values that are associated with it are anywhere from 0 to 5. So this is a basic frequency distribution. This tells us that out of the total number of people, 214 who we surveyed, let's say, had no siblings at all. 32 people had 1, 122 had 2, 45 had 3, 23 had 4, 4 people had 5. You should be asking yourself, what's the modal number of siblings? And you should immediately see that it's surprisingly 0 in this case. The most common number that was given was 0. And the way to calculate this frequency distribution, there are too many people to write out all the raw data and add it up, but you can obviously do it a slightly different way. One thing we do have to establish is what is our n? What is our number of people? So we have to basically add up all of these numbers. All right, so here's our frequency distribution of how many siblings people have. So we have 214 people who have 0 and so on. We need our n though. So we have to add up our number of people over here. Calvin, will you help me with this? So 214 plus 32 plus 122 plus 45.
440.
440, okay. Oh, Louie came to say hi.
Hello.
We'll introduce Louie later. Okay.
Oh, don't hit the light.
So our n is 440. So when you think about our formula, it's the sum of each x divided by the n equals our x bar. So we have to add up all of our values and divide by n.
Okay.
So the way that we do this,
Do you want me to add?
Calvin, you're going to help me with this. Let me just move these over real quick. N equals 440. We'll come back to our formula in a second. So we're going to multiply 0 times 240, times 214, that equals 0. 1 times 32 equals 32. What's 2 times 122? It's 244. Uh-oh. Intruder. Go away.
It's 135
What?
for,
3 times 45?
yeah,
135. 4 times 23,
92,
92. And 5 times 4,
20.
20. So basically we're kind of simulating as if we're lining up all of our numbers. Sorry. Come here, honey. I'm sorry.
Louis, oh my gosh, oh my. Go, get down, get down.
He's fine. Keep her out of the way. We're simulating as if we're lining up all of our numbers in a row. And the easiest way to do that is just to multiply however many people got the number 2, however many people got the number 3, however many people got the number 4, and so on. This is how we do it. We have a frequency distribution if we have to do it by hand, which you do need to know. So let's add these up. Calvin, help.
The dogs were
It's
doing
okay.
bad stuff. Okay,
So 0 plus
32.
32 plus 244,
wait, 244 plus what?
135,
Plus what?
92,
20.
plus 20,
523.
523. Okay, and then, so that's basically the sum of all of our x's. And we're going to divide it by n, which is 440. So 523 divided by 440 equals what? You're killing me, dog.
What is it? 523?
Divided by 440.
1.188.
1.188. So I'm going to
Repeat
put, what?
Just 1.2, yeah.
I'm going to put 1.2 because I'm just going to round to the nearest tenth. So basically we're saying the mean of our sample, the average of our sample, the most typical number of siblings, all ways to describe the mean, is 1.2, which makes sense since we had our mode up here, so it was, somewhere right here is our mean. Simple, right? Yes. But again, I want you to be able to do this from a frequency distribution. All right, Calvin, can you go?
Okay.
Okay, so just a few limitations of the mean that we need to discuss. Number one, because every score or every value in a distribution is included in the mean, it means that every score affects the mean. Which means that if you have an unusual score at the top or the bottom of your distribution, it could throw off your mean value or pull it in one direction or the other. So let's look at two examples. You have 5 people,
Come here.
2 groups of 5 people. This group, they have incomes varying from $50,000 to $53,000 annual incomes. This group of 5 people, the first person has an income of $50,000, but the range goes all the way up to $1.5 million. So we see a much broader range, and in some ways you can see immediately that this person in this group would be considered an outlier. So let's see what, and then what happens is if you take the mean or the average of this group, it's going to be much lower than the mean or average of this group, which is going to be really pulled, or what we say skewed, because of that one score. So that's what we mean when we say skewness or skewed. The mean is not good, really, and as useful when you have data that's extremely skewed by an outlier or a few outliers like that. In, atypical cases, basically. There are 2 kinds of skews I want you to be aware of. Basically, positive skew or negative skew. Positive skew means that you have an outlier that's all the way over to the right. So let me give you a few examples of situations where you would see a positive skew. Let's say, for example, that you took a test and that it was extremely difficult, all right? So on the bottom would be all of the grades that you got on the test. So if you kind of look at this distribution and say F is like here, most people then failed that test. So this is the number of people who got each of the grades. But there were a few people, for some reason, who did extremely well and got A's. So they have skewed this distribution where most of the class was right here. And those few people skewed it because they did really well. Another example might be, I have here length of prison sentence. Most people who go to prison probably have prison sentences within, a few years or less. And but of course you have a few in there who are, say, lifers, life in prison, and they're going to skew the data set in that way. One other example I'll give you, income in the United States is notoriously a skewed situation because you have a few people who are, say, the billion trillionaires, whereas everybody else, in terms of their income, is on the lower end. The average income in the U.S. family household income is probably around 50,000. Where, so if you were to report the average, those trillionaires up there are going to make it seem like the average income is a lot higher than it truly is in terms of the most typical income, which is why you always hear people say they'll report the median income in the United States, because it's a more true representation of the data. Okay, let's look at example of negative skew. So negative skew is the exact opposite. It's where you have most of your data at the higher end with a couple of cases down at the low end. So let me just give you a few examples of this. So if you had a really easy test, for example, most of the people, their grades would be up here in the A pluses, or near 95%. But there were a few people who just didn't have a good night's sleep, weren't feeling well, completely lost in the class, and they got some Fs. So they kind of skewed that distribution, and as a result, your mean is going to be probably around here because of those few people. So it's not going to be a great reflection of the true distribution of data. Here's another example, the age at which people die. So we have most people, their life spans are going to be up here, and the average is probably in the high 70s, low 80s. But you do have some people who die younger, and so they may skew that average if you include them, for example. So that's an example of a negative skew, just to demonstrate how a few outlying values can really affect the mean. Just a few more colorful examples of what the relationship would be between the mean, the median, and the mode if you have a positive skew. This is the relationship. The mean will be here, and the median and the mode will always be to the left of the mean. Because you see the mean is being pulled in the direction of those outlier values over there, which is why you'd find, say, the median or even the mode to be a better characterization of a typical value in this data set. And so in red, it's saying when the mean is higher than the median, then you have a positive skew. When the mean is lower than the median, or to the left of the median, you have a negative skew, so it's being pulled in this direction. So you see how you really have to have a good sense of what a frequency distribution, or what the line graph really represents in order to understand this graph. You have to know that this y-axis is the number of cases, it's not drawn here, and that the x-axis is representing values. So we're going to be utilizing this kind of visual representation of data throughout the entire semester. So I want you to get super comfortable with understanding what it means. Okay, so this is the chart that you all have to fill in, and here it is filled in. So in bold are the situations where you have a measure of central tendency and where it's most appropriately used. And as you can see, the mean is most appropriately used with interval ratio. And I put this in red that a lot of times people will try to use it with ordinal data, but technically it should not be. So kind of memorize where these bolded yeses sit, especially. Know where all the yeses fit, but particularly where the bolded yeses are, in terms of what's most appropriate. Okay, I'm going to do that. All right, so that's it for measures of central tendency. I'm going to take a little break, and then I'm going to go into start discussing measures of dispersion, see how far I can get this evening before passing out. So this is Louis. He's my helper. He helps me grade papers. He's a good boy, right? He's a very good boy. Okay, Louie, you ready to learn about measures of dispersion? Yes? Okay. All right. So you all have class objectives for this from 118, the day we missed for snow. We're caught up with this. We learned about measures of central tendency, and we know that they tell us the location at the center of a data distribution. The mean, median, the mode all tell us the typical average or central score of a data distribution. However, that can only tell us so much. A lot of times we want to know about distributions in other ways, because you can have very different data distributions that have the same central value. I'll give you some examples of that in a minute. So, the way that we can also describe distributions of data, raw data, basically like if you had two different samples of data or two different groups of people, it tells you how dispersed the data is. That's where we get the word dispersion. How much the data is sprinkled around the mean. How similar or dissimilar a set of scores are to one another. So you could be looking at, one sample of people, but a lot of times you're using this kind of measure to compare one sample to another. And some of these measures we're going to look at, typically a smaller score, smaller value indicates less variation in the data, which means that your mean is actually, a pretty reliable number. And then the larger that number is going to be, it tells you that there's a lot more spread of data around the mean. It's more spread out. Another key point here in red on the bottom, measures of dispersion are only for interval ratio variables. Some people treat ordinal variables that way, but we are only going to think about them for interval level variables. Okay. So, here's an example of, let's say this is IQ. No, let's say it's test scores. Test scores. So we have these test scores on our x-axis. Somebody got a 35, somebody got a 70, somebody got a 100. Of course, we get this whole range. Somebody got a 0. And this tells us about the number of people who got these grades. The reason we have 3 different lines here is that that's 3 different classes. Let's pretend it's class A, class B, and class C. All 3 statistics classes. And then this N, well, don't worry about the N. Anyway, the question is, which of these classes, oh, he has here math scores, which of these classes has the larger dispersion, meaning more spread out around the mean, assuming that the mean for all 3 of these is 70. We can see that this class has a more spread out in terms of how you would, visualize this data if you were to draw a line around it. We have people who are really getting grades all along the spectrum, whereas people, that would be class C, whereas class A, they're much closer to the mean. We don't have anybody in class A who actually got 100. You see? Nor do we have anybody in class A who got a 35. They're much more around the mean. So we have 3 different classes. All 3 of them had an average of 70, but the behavior, in terms of everybody's scores is very different. So the mean doesn't really tell us that much about that kind of variation that went on in that class. Which class would you want to be in? Would you want to be in the class where nobody got 100? You'd be more likely to have gotten a passing grade if you were in class A. So just something to think about in terms of just the idea that the mean can be a distraction sometimes in terms of really telling us something about how the data was distributed. So there's three measures of dispersion that we're going to talk about. The first one is range. It's very straightforward. It's simply the distance between the lowest and the highest values in a data distribution. And typically you figure it in terms of you just take the highest score that people would have gotten and subtract it from the lowest score. Or excuse me, take the highest score and subtract the lowest score from it, and you get one value, which is the range. So, and the higher that number is, of course, the greater the variation it implies in the data. So if you go back here, the range for this C data set would be 100 minus 35. That's going to be a much bigger number than if you took these values and subtracted this one from this one. So it's a really simple thing to use. It does not use all the data points, but it's a really quick and easy way to gauge what that variation would be. Okay. All right, moving on. So, suppose I gave the same test to two classes, and I want to know how well each class did. And the question is, which statistic would I use? Probably I would look at the class average, or the mean, to get a sense of the difference. But as I said before, there's a problem when you look just at the average. And that problem is that you can have the same mean, right? But it doesn't tell you how dispersed the data are. So let's look at two classes. We have this class and we have this class. And here's their raw data for their grades. Let's see. Okay, so for both classes, they have a mean score of 75. Now, if you look at this class, you can see everybody got in the 70s. So it really makes sense that you would see a mean of 75. When you look at this class, look, somebody got 100, a 99, a 96, a couple people got Fs, but they also got a 75. So, there's a wild range here that is not reflected in the mean. And these two classes clearly had different levels of comprehension across the board. And so the mean does not give us that information. So there's a way we can figure out, based on measures of dispersion, what was that variation in each class. So the first thing we want to do is come up with what we call a deviation score, which essentially is how much did each of the scores, or observations as we call them, how much does each of them deviate from the mean? So this just simply means individual scores. So we can subtract the mean from each one to give us a sense of what that deviation is. So obviously if D is small, it means it's close to 0. It means that the deviation was small, the dispersion was small. If it's a lot different from 0, far from 0, either in the negative or the positive direction, we know that that score was really far from what the mean was. So if we take the two classes and we subtract the mean, which was 75, from every single score, you can get a sense of how far every score was from the mean. So 79 minus 75 was 4, 78 minus 75 was 3, all pretty low numbers. And, if you could just sort of ignore the negative signs either way, they're low values. Whereas over here, you subtract the mean from these scores, you have very big values because, 100 minus 75 is 25. Obviously the only one that's going to be 0 is the one that's right on the mean. So what we want to be able to do is take an average of all these to give us a sense of the overall difference of all the scores from the mean. The problem is we can't just add them up because they're always going to equal 0. That's something I want you to know. If you add up all these differences from the mean, they'll all always equal 0. So you can't do that. It's just the nature of the mean. The mean's the center. Some scores are going to be above it, some scores are going to be below it. So if you add up the differences between the mean and every score, it's always going to be 0. So that is basically saying the sum of all of the positive deviations plus the sum of the negative deviations are always going to be 0. So we have what we call a tool called the variance, which basically takes all of those deviations that we just did and squares them and then divides by, well, we could divide by n, but when we're dealing with a sample, we need to divide by n minus 1. We don't need to really get into why we do that, but it's kind of a data correction. Again, don't let the formula scare you, but again, we have the summation sign, which is saying just do this over and over for every piece of data, and this is that d that we were just looking at. This d is the same thing as the x minus the mean. So for every value that we have, you're going to subtract the mean. Now if you remember back from our previous one, we have negative numbers. So that's why we're going to square each one to cancel out those negative numbers. And then we're going to divide by our n, essentially, to get an average. So same concept as kind of what we did when we got our mean. We're just finding our mean difference, basically. And again, we're squaring this because we want to get rid of all those negative values, and then we're going to take the average, or excuse me, we're going to divide by our n, which in this case, I forget, what was it? Our class size, well, let's see, 1, 2, 10, class size was 10. So then we call this the variance. And this is our symbol for variance, is s squared. So here it is. Exactly what we just did before. This time, we're going to square each and every one of those.
Go.
Okay, so I promise we're almost done. So here we have the variance, and the one thing that we need to do to it is to adjust it so that it better reflects these actual values, because when we squared it, we kind of blew it up. So we have to sort of unblow it up by taking the square root of it, and that's all a standard deviation is. The standard deviation is the square root of the variance. And what it does, it is just puts it into the units, the original units of whatever value you had, whether it was test points or whatever the variable was. So that is the formula for standard deviation, which all that is the variance formula that we just went through with the square root above it. So we take the square root to bring us back to the units we started with, and oh shoot, we don't have a square root value for that. Oh yeah, we do. Okay. So just a couple notes before, well, let's look at that. So here's the whole thing, and when we take the square root, we see that the average amount that every score deviates from the mean is around 2.5. But for this sample, the average amount that every score deviates from the mean of 75 is 16.9. So because this is bigger, there's more variation, there's more dispersion in that data. So here's a couple other notes about standard deviation. It has a minimum value of 0, which you would get if all the scores were exactly the same, because if you subtracted every score from the mean, which if every score is the same, there's not going to be any variation at all. As I said, a larger value indicates more variation, and then that value should be interpreted in the units measured. So if it's a test score value, if it's, if you're talking about, if the variable you're measuring is like number of drinks, or, something like that, then, that's your standard deviation score is the same. So it just relates back to whatever variable you're representing in your data. Okay, what we're going to do on next class is to go through that, a couple more examples of that. You're going to be able to practice that yourself. It's the only thing that, mathematically that I want you to be able to compute yourselves. I'll give you the formula, but I think you just need to intuitively understand how it works. So we'll go through that again when I see you. And please bring questions, and I hope I did not bore you to tears. Have a good night.